So if you took, a dust, spherically distributed ball of dust, and you allowed it to collapse, then you can form a Schwarzschild solution, and that's something that we described. That's the Oppenheimer-Snyder solution. And then, at the end of the last lecture, I also told you about these other black hole solutions, one of which is this charged Schwarzschild solution, and the other is a Schwarzschild solution with angular momentum, which is called the Kerr solution. And then you can put charge on those solutions as well, and that's called the charged Kerr solution or the Kerr-Newman solution. So that's what we've done so far. Are there any questions from yesterday? Okay. So, yeah.
So far is static black hole solution.
And stationary black hole solution, yeah.
So non-static, what is the equation?
So actually we didn't, we haven't only done static black hole solutions, because we actually did the collapsing black hole solution, which was a solution which, was not something that was time independent. Where we started with something, there was a very dynamical solution that we found. So that's an example of something that's, that's a solution which is formed by dynamics. Of course, at late times, all of these solutions tend to settle down. So they tend to settle down into a solution that's stationary, not necessarily static, which means that things roughly become, time independent, and the physics becomes time independent, and that's the statement of, that's just a statement that you tend to get from the fact that things tend to settle down into equilibrium. So that's, we haven't actually only dealt with static solutions. The Oppenheimer-Snyder solution is not static. That's the solution we found. Okay, so there was a question I gave yesterday, which I believe nobody did, which was a question of the Q by M ratio of the electron. Did someone work the solution out? Did someone work out the Q by M ratio? Okay, it's not such a hard problem. Let me just tell you how you do it. You see, you have to look at. Here's one simple way to do it. Think of an electron. Okay, think of two electrons, and which have some E and M. Sorry, it could be an electron or a proton. Okay, and one way to compare this ratio is to look at the ratio of the electrostatic, force between them and the gravitational force between them. Right. So if you look at where K is Coulomb's constant, if you look at Ke squared by R squared, this is the force, and if you look at Gm squared by R squared, this is the force. Right. So, the ratio of these two numbers gives you a dimensionless number. Therefore, Ke squared by Gm squared is dimensionless. And clearly, if you take the square root of this, you'll get the ratio. Right? So if you take the square root of this, that gives you E by M into square root of K by G, and you just have to compute this number. So it's not actually a hard problem, and it's actually very important. I really want to encourage you to put in these numbers. Often when we are doing a general relativity or quantum field theory, you set h bar equal to c and so on equal to 1. But it's very important to actually put in these numbers and get a sense of what are the numerical things that we are talking about. And I'll give you more of such numerical problems, and I really want to encourage you to get familiar with just restoring factors of Coulomb's constant and Newton's constant and so on. Does someone know what this ratio is? The ratio of the force? Good, very good. So it's about, so this force is about 10 to the power 1. Okay, that tells you that this number is about, 10 to the power 20. Actually, it's 10 to the power, 18 for an electron and 10 to the power 21 for a proton. But it's 10 to the power 20 is about right. So notice, by the way, that this is completely in violation of the criteria that we had yesterday, which was that, remember for a Rice-Nostrom black hole, we had a criteria that M had to be larger than E, and this is completely violating that criteria. So there's no sense in which, fundamental particles are black holes. They don't satisfy this criteria. Okay, so now I have another question for you to think about, which is the following. Okay. So take a so M larger than E, and then start throwing electrons into it. Okay, what happens? It's a slightly open-ended question, but the question is, can you actually violate this bound by throwing electrons into a Risonov? You start with a regular Risonov-Strom solution. You can even start with a Schwarzschild solution, and then start throwing these electrons into it. They have much more charge than they have mass. So you might think once you throw some number of electrons into it, enough number of electrons into it, you would violate this bound, and therefore you would have generated a solution which has mass smaller than charge. Because each of these has mass much smaller than charge. So is the question clear? We have a bound and physical solutions. We have fundamental particles which satisfy some totally different relation. Now start with the Risonov-Strom black hole with mass larger than charge. Or start with a Schwarzschild solution which has no charge and start throwing electrons into it. And eventually, naively, one might have thought that you would come up with a situation where you would be able to violate this bound. You throw enough electrons and you would violate the bound. Okay, so the question is why can you do this? Is this possible? And if it's not possible, why is it not possible? Okay, so that's something to think about. Okay, very good. Are there any other questions from yesterday? Okay, so now at the end of yesterday's lecture, I mentioned the no-hair theorem. The no-hair theorem is a statement that if you look at asymptotically flat spacetimes and you demand that these spacetimes are stationary, then the most general solution you can find is a charged curved black hole. Okay. So and this statement is called the no-hair theorem, and we won't go into the proof of the statement, but just we'll take it as a fact that this is the case, and you can try and prove these results. In fact, as I said, if you look at the the APS Centennial papers that I mentioned, that I've been mentioning repeatedly in this class, there's a paper by Israel which proves a weaker result, which proves that if you look for static solutions, then the unique static solution that you get is a Schwarzschild solution. And in fact, if you look for static solutions with charge, the unique solution you get is a Risonov-Strom solution. So look at Israel. This GR Centennial correction in APS, and look at Israel's paper, which proves the version of this. This statement is slightly stronger than what Israel proves. But if you'd like to look at the proof, how the proof is done, this is one paper to look at. And as I said, this is a very useful collection of papers, which you look at otherwise as well. Okay? Now, what is the significance of what's the significance of this theorem? The significance of this theorem is that we might have thought that you can form black holes from all sorts of initial data. Right? You can take a black hole. You can take this bag and you can collapse it into a black hole. You can take the spherical ball of dust that we had yesterday, or you can take some other configuration of matter, and you can collapse things into a black hole. And then, as I said some time back, you expect that after a long time things will settle down. You might have thought that maybe things won't settle down because some things will stay orbiting. You might get planets or Saturns or things like that which are orbiting around the black hole. But in fact, all of these situations tend to decay the moment you include gravitational radiation. So you can't have gravitational atoms just like you can't have purely electromagnetic atoms. And therefore, all of these configurations tend to decay, and they tend to settle down into something that's stationary. And the most general stationary black hole is the Kerr-Newman black hole, which has only three parameters. It has the mass, charge, and the angular momentum. So the significance of this theorem, which is something that we'll explore much more in the second half of the course starting next week, is actually that it looks like black holes have no way of preserving the initial information that went into them. You could take this classroom, and this classroom has a lot of information, all the books and all the information in our brains, and you could collapse it into a black hole. And when you collapse it into a black hole, in that process there would be some gravitational radiation that would get sent out. But not all the energy would get radiated out as gravitational radiation, and in fact maybe you could arrange things so that only a small amount of energy is radiated out as gravitational radiation. So then, a large amount of the energy has been captured into a black hole. But whereas the initial matter distribution had a lot of features it looks like the black hole has no features except for the mass, charge, and angular momentum. So this is already leading us, to some sort of paradox, because it's suggesting that you can start with, various kinds of initial data and end up with the same final state, and that's something that seems to be in conflict with reversibility. And this is what we'll explore next time. Yeah.
What would happen if there is a cosmological constant?
Good. So I'll discuss that. 1 second. Yeah. Okay. So So this is apart from that question, which I'm coming to next. Are there any other questions about the Snow-Hair theorem? Is the significance of this clear? Okay. If you have any questions about this, feel free to ask. Yeah.
Why it is only mass charge and angular momentum and no other parameter?
That's right. That's the theorem. That you want to look for stationary solutions.
Why is only these three parameters? It can be any.
What other parameters? The theorem is that you don't have any other parameters. You might have thought that you could take some scalar field and give some profile of the scalar field on top, or you could take the shape of the horizon and that could be a parameter. You could have thought that there could be lots of, in principle, that you see, if I give you this bag and ask you to characterize the bag, the bag has a lot of properties. Okay, there's a mass to the bag, but there's a shape to the bag. There's an entire shape to the bag. So to characterize the shape of the bag, you need a lot of parameters. You need some equation of the surface of the bag. So you might have thought that similarly, to completely characterize a black hole, you need an equation that tells you what the shape of the horizon is. Maybe there's some bag-shaped black holes and some bottle-shaped black holes and some other shaped black holes. But the remarkable theorem is that there are not. So you don't need all these equations to characterize the shape of the horizon.
But in everything you did, spherical symmetry is already assumed, right?
No, actually I didn't assume spherical symmetry. Actually, so the statement here is the opposite. The statement here is you're only assuming stationarity. So it's true. The first day I proved the result that spherical symmetry implies static. Anyway, the difference between static and stationary is roughly explained in the following way. A stationary solution is where nothing meaningful is changing with time. So you could have, as sometimes people say, you could have water flowing in a pipe, and that's a stationary solution if the velocity is not changing. Okay, so just things are flowing. There's some velocities, and things are not. Nothing is changing with time. Nothing meaningful is changing with time. A static solution is one where there are no velocities. So this is a question, which is formally defined in terms of having time-like Killing vectors, which are either hypersurface orthogonal or not. But the physics of whether something is the difference between static and stationary is really the difference between having water flowing with uniform velocity or having this water stationary at some point. And so in any case, if you look at the simpler solution, which is static solutions, what I proved the first day was that spherical symmetry implies static. The Snow-Hair theorem is the other statement. It said static implies spherical symmetry. Okay, so this statement we have not proved. This is what we proved, which was Birkhoff's theorem. And this is the Snow-Hair theorem. So we proved this side, we haven't proved this side, but this side I'm giving you as a statement.
Does it have to be spherical? Curve is not spherical.
No, so static implies spherical symmetry. So static is not stationary.
So what about temperature or surface gravity?
So temperature and surface gravity is all part of these, which we'll discuss today.
This is just because we are looking into a thermodynamic system, like the black hole. Once you start with something with a profile like a scalar field or etc.
No, it's still true. Even if you start with a scalar field, you don't have these things. Maybe you're thinking of, I don't know, are you thinking of these ADS solutions?
No, in the sense that if you're looking at the full microstate picture or something like that, shouldn't it be naturally resolved?
No, it wouldn't be naturally resolved. You don't have, if you add scalar fields and so on, it's not like you can get scalar hair on top of a black hole. There are these solutions which people talk about nowadays where you take ADS and you try and get scalar hair on top of black hole. These are actually fake solutions. There's a fake hair because what you're doing here is you're in some sense holding, you've turned on some chemical potential. So you're holding the value of the scalar field fixed with some additional external force. So of course if you do that, then you can generate hair. If you insist on adding some external force, a chemical potential that holds a certain profile of the hair fixed, then you can get hair. But if you don't do that, then you don't have.
That can't be done in asymptotically flat spaces.
That can't be done in asymptotically flat spaces also because you can't hold things fixed. So in ADS, the existence of a boundary allows you to hold some profile. But yeah, in asymptotically flat spaces you can't do that also.
So
Guessing this holds for quantum as well. I mean, even at the level of microscales.
No, there's no statement about quantum. This is just a statement about classical solutions. Yeah, the quantum physics is something totally different. I'm just making a statement about classical solutions. Okay. Okay, so good. So this is called the no-hair theorem. And, I should say that there's one more way of thinking about this no-hair theorem, which is that, you could take it in two ways. One of them is that, if you think of some system of particles, in general, a system of particles interacting under electromagnetism also doesn't form something stable. You need quantum mechanics to give you stability of matter. In some sense, if you look at stable solutions in electrodynamics, these stable solutions have the form of what are called solitons, which are usually protected by some topological charge. In some sense, what is special about these black hole solutions is that they are solitonic solutions that are not protected by a solitonic charge. So in principle, they could decay to something, and it's true they can be formed from just ordinary systems without having any special topological charge. But the statement is that there are these solutions which have a lot of energy which are stable, and there's only a finite parameter family of them. So you can take the no-hair theorem in either way. You could have taken the other attitude and said that electrodynamics, if I take some system of electrons that are interacting, in general these systems don't form something stable. They either go off to infinity, or they all collapse into each other because of just electromagnetic radiation. And unless I have quantum mechanics, I can't form stable atoms. But here you can. You do get these stable solutions. They do carry a lot of energy, but they don't carry information, and that's what's surprising. You would have thought that if you have solutions which have a lot of mass, they also carry information about how the mass is distributed, and these solutions don't. So that's what's surprising. Okay.
So if there was some scalar field which was coupled with the...
yeah, it doesn't change the situation.
So then the scalar field has to decay once the black hole starts.
That's right. So what will happen is generally if you have the dust band that we formed yesterday could have been formed out of a scalar field. So we looked at an Oppenheimer-Snyder collapse solution. I didn't tell you what the matter was formed of. You could have taken some kind of scalar field and formed it. And then all of that collapses into a singularity, and maybe some of it gets radiated away. But you can't get profiles of the field on top of this. Okay, good. So now someone asked a question about a cosmological constant. So what happens if you modify the asymptotics? In fact, not too much morally different happens, but you do get some new solutions. And I'll describe those solutions because they're very useful the moment we start discussing the quantum physics of black holes. So I'm going to describe to you what these solutions are. So if you add a cosmological constant, the equations of motion become so this lambda is called the cosmological constant. Now, what is the significance of lambda in terms of what we've been talking about? You see, what a cosmological constant lets you do is it lets you modify the asymptotically flat boundary conditions that we've been assuming so far. Now, if you wanted to modify the asymptotic structure of space-time, you need some energy that exists out at infinity, right, which can cause curvature of space-time out at infinity. Now, you don't want to put in an infinite amount of matter that will cause this, because any configuration of matter that you take is generally confined. You have a finite energy solution. So, if you really want to change the asymptotic curvature of space-time, a convenient way to do that is to look at what's called a cosmological constant, and you can add these to Einstein's equations consistently, and you find that you get these equations of motion, and this constant lambda is called the cosmological constant. Do you know what the value of the cosmological, whether it's positive or negative for our universe?
Negative.
Okay, so right. So in these conventions, by the way, there's a bit of a convention. In these conventions, our universe has well, we don't know if it has. We don't quite know if it has a cosmological constant that's positive. But we do know that the expansion of the universe is accelerating, and that's consistent with lambda positive. It doesn't imply it's not the only way to get an accelerating expansion, but it's one of the simplest ways to get an accelerating expansion is to say lambda is positive. If you look at so if you just look at the vacuum solution with lambda positive, that solution is called de Sitter space. So if you look at this is actually not the solution we will be looking at. You might have thought that we should be more interested in the solution because this is how our universe is. But it turns out that looking at situations with lambda positive is actually harder for various reasons, which I'll try and motivate maybe at the end of this lecture and later, than solutions with lambda negative. And so you want to look at solutions with lambda negative, and this is called anti-de Sitter space. Okay. So if you look at vacuum solutions with lambda negative, the space that you get is called anti-de Sitter space. And it's actually very useful, as I'll show you in a minute. I'll try and describe why it's useful, but for now, let's just explore what happens if you take solutions with lambda negative. So I'm going to write down the solution, and I'll tell you how the solution works. All of you have now hopefully seen how to use Mathematica to check various solutions and compute various components. And so I'm going to give you a solution, and you can verify that it actually is a solution. So the solution is as follows. And then write down the x square. Into d omega square. The omega square is our usual this L is related to that constant lambda, where lambda is minus 3m squared. Okay. There's a constant L, and the reason you choose this constant L is called the ADS radius. Okay. And often it's convenient to set L equal to 1 rather than lambda equal to 1. So you could work in units where you set lambda equal to 1, which just sets a scale. But it's often convenient to set L equal to 1 and work in terms of units of the ADS radius. That's this constant that appears here. Okay, so this I claim is a solution of Einstein's equations with this value lambda. So I'm just stating that this is the solution. And this is called the ADS Schwarzschild solution. So if you change the asymptotics of space-time, you get new kinds of solutions which look like this. You can see that asymptotically these solutions don't look like flat space. They don't look like flat space because if you take large R, you see the term you get is that it looks like R squared plus 1 into dt squared plus dr squared by r squared is 1. Okay, and that's very different from flat space. So notice that there's no limit in which these solutions start looking like flat. I mean, there's no limit of R in which these solutions start looking like flat. So the asymptotics of these things, which is what happens at large R, is what's called anti-de Sitter space. So if you want to get ADS, you just set m to 0, you'll get the empty ADS solution. And without setting m to 0, I'll just call the ADS Schwarzschild solution.
So m is set here using conserved quantity.
M is just better. So m is the mass.
You can't do asymptotics like
You can do asymptotics. You have to define the mass slightly differently. You have to basically the mass is always defined asymptotically, but you have to do an integral on the boundary of ADS, and you have to ask, what happens if you had a mass at the center of ADS, and what the Newton's first law would be. Using that, you can define m. Again, asymptotically. Mass is always defined asymptotically, except here it's asymptotically ADS rather than asymptotically flat space.
So what is the ADS radius?
It's just a constant. It's related to this lambda. If you set m to 0, then you get a solution that looks like r square by l square plus 1 into this. So the constant that appears here is called the ADS radius. It's just a definition of the constant that appears in the anti-de Sitter space solution. You see, if you set lambda equal to 0, so let me write it down. So you see, I said lambda is equal to 0 is anti-de Sitter space.
Suvrat,
This is the solution.
just one confusion. So I was just trying to see the dimensions of these things in HL units. So lambda has, so if I take H
L has dimensions of length,
M
has dimensions of length,
but lambda has dimensions of length to the power, mass to the power 4, right?
Oh, yes, 1 second. So you're saying that there should be an L, so there may be some G Newton which I've missed there. So I've said this is in units where m Planck is 1. So if you set m to 0, you said you get So this is the ADS solution. And you can take the solution and you can ask what is the value of lambda for which it satisfies the equations of motion payload. And it satisfies the equations of motion for lambda is equal to minus 3s. Yeah.
If I set in this method, if I set lambda to be 0,
lambda to be 0.
I should get that cross shell, right?
No, so setting lambda to be taking the flat space limit of ADS is somewhat more complicated. This is the solution. No, taking the flat space limit of ADS is more complicated. What you need to do actually is take L to infinity in a sense. And then so taking the flat space limit is a more complicated story. Because these black holes have a Schwarzschild radius that scales with the ADS radius. The Schwarzschild radius is order 1 in these units. The Schwarzschild radius scales with the ADS radius. So these are what are called big black holes. So if you try to take, taking the flat space limit is more complicated. So you have to take the flat space limit more carefully. You can do that, but you have to look at different kinds of solutions, and then you can take the flat space limit. There's a sense in which flat space is embedded in ADS, and that's a sense in which when you look at physics, which is where the scales at which you're looking at physics are much smaller than the cosmological scales, and then things look like flat space. Which is, for example, what happens in our universe. We have a cosmological constant, but locally things look a lot like flat space. But on the other hand, if you started looking at cosmological scales, at black holes which were as large as the cosmological scale, which is what this is. This black hole is a black hole which is as large as the cosmological scale. Then it's much harder to take the flat space. You have to be much more careful in taking the flat space. Okay, are there any other questions about the solution?
So where does the A term come from?
Where does what term come
How
from?
do we get an A term in that case?
Oh, what term?
The A term, it's a constant. So if
A term?
the A term and the last part.
A term. It's just a constant. How to say it?
So there's no significance to it, or is it?
There's some, in general, there's some more complicated constant. It's some dimension-dependent constant. In general, it's pi to the d by 2 into gamma of d by 2 plus 1 or something. So if you look at ADS 4, it's 8.
Isn't it alpha minus 2 plus lambda?
L power minus 2. No, I don't think so. I don't think it's L power minus 2.
Is this a vacuum solution?
This is a solution with a cosmological constant. So it's not the vacuum.
It's not a vacuum.
Not a vacuum. Okay, good. So now, we want to go back to analyze the causal structure of these solutions. So now I'm going to take a step back and analyze the causal structure of all the solutions that we've done. We already did in some detail the causal structure of the Schwarzschild solution. So now I want to analyze the causal structure of the Reifson-Ostrom solution. So actually, I want to make
one doubt. So if it's not a vacuum solution, then what does this mean?
Oh, sorry. Vacuum means no stress tensor. It's a vacuum. It means that the stress tensor is zero. That's no external matter, but there is a cosmological constant. So it's not vacuum in the sense. You're right. So what I wrote here was confusing. It's vacuum in the sense that T mu is zero. It's only lambda.
So it is a vacuum solution in that sense.
That's right. In that sense, it's a vacuum. It has a cosmological constant, but no stress.
I mean, but it's not a solution of the general Einstein equation, but it's the solution of the Einstein equation with cosmological constant.
What do you mean by general Einstein equation? It's a solution of these equations.
I mean, general means the usual. It's a solution of this.
Of this.
Barkhoff's theorem holds there.
No, this is so Barkhoff's theorem holds. Barkhoff's theorem was a statement about what happens if you have R mu is zero. That doesn't happen. Okay. Are there any other questions about this? Okay. So now I want to take a step back and ask about the causal structure of these solutions. So I want to go back to the Reifson-Ostrom solution that we had, and I want to describe the causal structure of this solution. so remember this is the solution that we had, this is the Rice-Nordstrom solution. And now, to look at the causal structure, there's a, if you really want to look at this in detail, there's a paper by Brandon Carter, which is called analytic extension of the Rice-Nordstrom.
Sir, is that 2m by omega?
Is what omega?
No, it's
R. Oh, sorry, my handwriting is bad.
Yes, sir, there is two types of R, so I am confused.
This is omega and this is sorry. Sorry about that. Sorry, there are two types of R's also.
Also dr square, so you should change.
There's a dr square. So, sorry, my handwriting, as you can see, is very, very bad, and I'm bad about this. So I hope you'll excuse me, and it should be clear from the context what's omega. Omega always appears in this sphere. Okay. So it's true, my R looks like an omega, and I write R in different ways. But, thankfully, I don't have to give any exams anymore. It was a nightmare, obviously, when I had to give exams, and the examiners also, thought I was really writing omega instead of R. So anyway, if you look at Carter, there's a complete analytic extension of the Rice-Nordstrom solution, and you can look at that paper if you want. Yeah, but I'll just try and describe, what the essential points are. Now, the main point is to introduce once again a tortoise coordinate. Okay, the trick of how to understand this is to introduce a tortoise coordinate, and the tortoise coordinate is once again introduced. Remember to make this part, the dt dr part, look uniformly flat, and so that's the statement that you want to introduce a coordinate that has this property, right? Only the R's, okay? I'm not going to write an omega now. Okay. So you want to introduce a coordinate that has this property, and if you can solve this equation, you'll find that maybe we can now that you pointed this out. This 1 by r plus into r minus divides this. Okay, so it's a simple differential equation to solve. Remember that this you can factorize as r minus r plus into r minus r minus, as we discussed, which we did discuss, I think, at the end of the last lecture, right? Did we? This quadratic term has roots which are r plus and r minus, which I think I wrote down at the end of the last lecture. And then if you solve this equation, you find it's r plus 1 by r plus into r minus, and this is multiplied by this bracket. Okay, so I didn't have space on the board, but this term is multiplied by this bracket. This is the solution for the tortoise coordinate. Now the trick is to look at the behavior of the tortoise coordinate as a function of r, and this behavior is somewhat different from what it is in the Schwarzschild case. So look at r, and here's r minus. What happens if r goes to infinity? What's the value of r as r equal to infinity? Okay. At r equal to infinity, it's infinity. What happens as we come to r plus? What happens to the value of r star as we come to r plus? You see, r plus minus r minus is positive. R plus is positive, and you see this goes to minus infinity, right? So this value, this term goes like this. And this is so far the same as what we've had in the Schwarzschild case. Okay. Then what happens is, this thing starts rising because this term comes into play. And so this term starts coming into play. And as r goes to r minus, as r minus by r minus becomes smaller than 1, this term, there's a minus sign outside, so this term starts giving a positive contribution. And therefore, this starts rising, happens at r minus is it goes off to plus infinity. Okay? And then from r again, it comes down and goes up to 0. Okay? So the behavior of the tortoise coordinate as a function of the radius is somewhat different from how it is in the Schwarzschild case. In the Schwarzschild case, this was r equal to 0. It went down to minus infinity and came up to 0 and it stopped there. It goes down to minus infinity, comes up to 0, goes up and then comes down again. Okay? So this is actually a quick way to see what the causal structure is. Because what you need to do is you need to introduce, as usual, okay, I want to say, by the way, that what I'm going to say from now is not, for the next 5 minutes, I want to give you a sketch of what the causal structure is, and then I want to make some points about it. You don't have to try to be very careful about trying to, the constants and so on that I'll use here are not particularly important, because as you'll see, in any case, the point I'm going to make is that this causal structure that we get is somewhat fake. Okay, so I just want to show you what the conventional causal structure people draw is and then tell you why it's fake. So now, we introduce our usual u and v coordinates, which are u is equal to e to the power r star minus e into some constant alpha. This constant alpha you have to set once again, in such a way to make the horizon regular. We're not going to bother with this constant alpha right now. Just repeat it in the Schwarzschild solution in exactly the same way. You can set this constant alpha to make the solution regular at r goes to r plus. Okay. Now it turns out that after this r star plus e, you remember we introduced we introduced at the end of the last lecture, we introduced these coordinates and inverse u. So these were the coordinates we used to draw the Penrose diagram, these chi and zeta coordinates. In fact, these coordinates, as Carter shows, are enough to cover the whole Dyson-Ostrom maximal extension. Provided you take them, you don't take them to range only of minus pi by 2 to pi by 2. But once you cross these boundaries, you're willing to go into other branches. Okay, so now what happens? First we have the region 1, which is the original Schwarzschild patch, and that region 1 is exactly the way it was. Now this is the solution chi is equal to 0. Okay, this u is equal to 0. This is the solution. This is the line zeta equal to 0. This is the line chi equal to pi by 2. This is what we are calling region 1, and this is the original Schwarzschild patch. This is what we call region 1 in the Schwarzschild picture, in the Schwarzschild Penrose diagram. And then you can try and follow the solution. As we said, you can extend the solution past this chi equal to 0 line into region 2. And then what happens? Now something more interesting happens, which is that as you extend it, you see that in the Schwarzschild case, what happened was as you extended it, lines of constant r, remember lines of constant uv, right? So lines of constant r are lines of constant u into v, lines of constant r star. Now in the Schwarzschild case, what happened was that we got a singularity inside region 2. The reason we got a singularity inside region 2 was that there was a point, once you go past this, which has uv is equal to 1. Okay? And that uv equal to 1 was in these Penrose diagrams, in these coordinates, some straight line, which was chi is equal to zeta minus pi by 2. And that gave you a singularity. So do you remember all of this from the Penrose diagram we had? Okay, so that gave you a singularity. But here, you see r star equals 0 is not a singularity. R star equals 0 is just some point between r plus and r minus. It's not the singularity at r equal to 0. Okay? So you can go past this setup here, and you find another diamond, which is now, so if you look at region 2, maybe I'll draw it here. So now if you look at region 2, you have this line which is chi is equal to 0. So this diamond sits on top of this one. Okay? So this is, I'm drawing region 2, it's going to sit on top of this one. Okay, and this is chi is equal to 0, r equal to r plus. You have a setup here which is zeta equal to 0, r equals r plus. This is the extension of this line. And then you can extend these things up to sorry, I made an inconsistency with my sign convention. We put a minus sign, so there's a minus sign here. But now you end up with, in this region 2, you end up with chi equal to pi by 2 and zeta equal to pi by 2. And this is the point where r is equal to r minus. You see what happens now, these lines correspond to uv equal to infinity, where either chi is pi by 2 or zeta is pi by 2. Okay? So you see, but uv equals infinity corresponds to r star equals to infinity, which happens at r equal to r minus. So am I losing you guys here? You see that uv tells you what r star is. U changes sign across this sign. Okay? So uv equals infinity is a statement that one of these is pi by 2. Either chi is pi by 2 or zeta is pi by 2. Okay? And that's the statement that r star is infinity, and that's the statement that you hit r minus. So this diamond, which is the diamond of region 2, you should place on top of this diamond. Okay, so this line chi equal to 0 and this line chi equal to 0 identified. And this is region 2. But there is no singularity in region 2. In fact, there is this part which is the inner horizon. This is r equal to r minus. And you can cross this inner horizon and extend the metric past that as well. Okay? So when you do this extension, then you will hit the singularity. Once you extend past r equals r minus, then you will hit the singularity at this point. But this singularity is now a time-like singularity. You see, the reason it's time-like is because you can have uv equals a minus number, uv equals a positive number. If you look at lines of uv, the hyperboloids here, of constant uv, which are lines of constant r star, those are time-like in region 1 and space-like in region 2. Right? And once you cross back into these regions, which you can call region 5 and 6, then they again become time-like. Okay, so I may be going a little fast, but I'm just going to tell you what the final result is. And if you haven't, this extension, if you go back and you look at it, you'll find it's not very hard to do. It's just a question of taking these UV coordinates and extending them. I'll tell you what the final result is, and the result is as follows. Now you get this causal structure. Which is as follows. And then the singularity is sitting here. And here. So this is region 1, region 2. Then there's a region 3. There's a singularity here, and then things keep extending up. Okay, so you can draw from here, these regions, and then they go up from there. And so these are what we are calling region 5 and region 6. So what we did was, what we have done, derived here is region 1, 2, and then I made it plausible that they are regions 5 and 6. Regions 3 and 4 exist just like they did in the Schwarz shell black hole solution. And then you can keep extending this solution some more into regions, whatever you want to call them, 10 or 7, 8, 9, and so on. Okay, so you get this, and the singularities are these ones. Let me draw the singularities instead. So it looks like if you take the Rice-Nostrom solution, and in fact these things keep going up. Okay, so this pattern keeps repeating. So you get more singularities on top. This whole pattern keeps repeating. So it looks like if you take the Rice-Nostrom solution and you try to continue it, not only do you get these regions, these regions 3 and 4 which we got in the Schwarz shell black hole, but you get an infinity of universes. Okay? Where you can keep going through these horizons and keep going up and up and up. So in fact a single observer, according to this diagram, can just keep traveling up and up while always avoiding the singularity into all of these different universes. Okay? So this is the Rice-Nostrom black hole has this extremely funny causal structure if you extend it maximally, which is that you have an observer, and the observer can follow some trajectory of this kind and can just keep going, jump into the horizon. This is the horizon r plus, this is the horizon r minus, okay? And you can just keep going higher and higher and without ever hitting the singularity. So this is a very funny kind of causal structure, but it is what comes out if you extend the Dyson-Ostrom black hole maximally. And it's also what comes out if you take the curved black hole. If you take the curved black hole and you try to extend it maximally, that analysis is more complicated. But once again, you get a solution which has this infinite number of universes. In fact, there the singularity structure is even more complicated. But the model principle is the same. You tend to get this infinity of extensions, and you get this very funny kind of causal structure. Okay. So what does this mean in reality? Now, I think that the important physical point I want to make. The fact that you get this is a question of doing some algebraic manipulations, and you'll see this figure in many textbooks. But there are two important points I want to make, which are not always made in textbooks. And so, if you haven't been paying attention so far, pay attention now. And these points are the following. Okay, this figure is fake for two reasons. Okay, it's fake for two reasons. One of them is that a collapsing shell this is the same as what we saw in the Oppenheimer-Snyder collapse solution. If you take a collapsing shell, it covers up these regions 2, 3, and 4, part of region 2, and covers up entirely regions 3 and 4. Okay. So if you look at the diagram we drew for the collapsing shell, it did not have any regions 3 and 4. Okay. But there is a second pathology of these solutions, and the second pathology is that this inner horizon so the horizon at r equals r minus is unstable. And if you make a small perturbation, in fact, this region collapses into a null singularity. Okay? So in fact, the true diagram is first of all that all these universes don't exist because their singularities at these points. These points which look like smooth horizons are actually not smooth. The inner horizons are not smooth and they have these instabilities, as I'll show you, I'll motivate in a second. And second, of course, all this left part doesn't exist. So let me motivate for you why the inner horizon is singular. You can look up, I think Chandrasekhar's book does a more careful calculation. But I'm going to motivate for you why the inner horizon is singular. I'm going to tell you what the physical reason for point 2 is. Okay, and point 2 is in some sense a point which is important and often underemphasized, I think, in textbook treatments of this Dyson-Ostrom solution. And the reason for this is as follows. Okay, so let's see. So let's say you have a massless scalar field in flat space. Okay, do you know what the Green's function looks like for the massless scalar field? What the retarded Green's function looks like for a massless scalar field in four-dimensional flat space? 1 by p squared. No, it doesn't look like 1 by k. Okay, what does it look like in position space? Okay, so the retarded Green's function in position space, what does it look like if you just take electrodynamics? How do things, how do the fields propagate? How do electrodynamic fields, how do massless fields propagate? No. It's much simpler than that. You see, the retarded Green's function has a form. No, it's even simpler than that. It's mod of x1 minus x2 squared. Okay, it's just delta function of the light cycle. So it's just delta of the interval. That's the statement that if you turn on a source here, okay, the source propagates at the speed of light. If you turn on a source here, there's an influence at this point. You're familiar with this if you've seen the linear Dirichlet potentials. Remember, the linear Dirichlet potentials involve taking, if you want to get the vector potential from a source, the way you get the vector potential is you evaluate the source at the retarded position. Are you familiar with this? Have you seen electrodynamics of moving charges? So what you do is you take a source and you evaluate the source. The solution is that you can write down in a certain gauge. A is equal to integral of J, but evaluated at the retarded position. So are you familiar with this thing? Okay. So if you're not, this is a useful thing to do in a. So maybe this is a. This is something we should discuss, which is check that this is the retarded green function. Then it looks like del dot lambda, and you can check it if it's basically the same as the derivation of the linear Bishop potential. The linear Bishop potential basically tell you that this is the retarded green function. It's the same statement. When you try to solve the Maxwell's equation, or trying to solve this, it's the same statement. Okay, good. So this is the retarded thing, which tells you that things. What this tells you is that things propagate along light rays in flat space. Okay, this is of course a statement which is true in flat space. It's not a statement here. This statement is not exactly true in the black hole background, but it does tell you, and this is actually an important thing which we will use once again later. So it's very important to have this clear. It tells you the following. Now, if I specify some initial data on this part, okay, this is my initial data in green, then the equations of motion tend to propagate this initial data along rays. If I turn on the source here, and this is my source, then the effect of this source gets propagated along light rays to to this point. So if you have massless fields and you turn on some initial data, or you turn on a source at some point, the information about the fact that you turn on that source tends to get propagated along light rays. Okay? And that's, in mathematical terms, the statement that the Green's function looks like mod of x1 minus x2 squared. Now this is a statement about flat space. This space has curvature. Okay? So of course the Green's function is more complicated. But the general statement is that at least if you're looking at waves of short wavelength which don't see the curvature, they tend to propagate along light rays. So are there any questions about this fact? This is a fact which I'm going to make a point here about why this horizon is unstable, but we're going to use this fact once again when we discuss Hawking radiation, so it's actually an important fact. So the explanation is, if you turn on the source at some point, there's space-time diagram. So this is X and T. Okay. The influence of this source propagates along light rays. So if you turn on the source here, the fields that the source creates, if you use the retarded Green's function, are created along light rays that emanate from this point that go out into the future. Okay. So if you turn on a source in the past here, at some point here, remember this is what we are calling past null infinity, then this information propagates in light rays, which reaches here, just like if you turn on a source in a space-time diagram. As a result of this Green's function, this information propagates in light rays, and this information also propagates in light rays. By the way, we could do all this much more formally by solving the wave equation. I didn't want to do that because I want to give you a sense of the physics, so I don't want to get into solving the wave equation. So the physics is that information tends to propagate along light rays, just like information in flat space for a source, electrodynamic source propagates in light rays. Information here also propagates in light rays. Okay, so if you give me some initial data, remember this is what we were calling past null infinity. So if you give me some initial data in the past, the effect of that initial data propagates along light rays. Okay. Now what happens? Now notice that there's something very funny that happens.
So this fact is true in curvature also, right?
But this fact is not exactly true in curvature. It's true for short wavelength, modes in curvature, which don't see the curvature. But it's a good way to get what we want. What I want to make right now is a qualitative statement.
But these null rays are also geodesics.
Correct. But if you solve the full wave equation in the presence of curvature, you get something more complicated because fields tend to couple to curvature. And therefore, they behave a little bit like massive fields, and therefore they don't propagate exactly along light rays, but they tend to spread inside the light cone as well. But those complications are not important, and that's why I don't want to go into solving the wave equation. Okay. So, it's a good approximation that if you look at short wavelength modes, these modes propagate along light rays. Now we're going to come back to this in 2 lectures from now. This is something which is important and which you should hear about. Okay, so now what happened? Now notice the following funny thing. Now, even though we've drawn this, in terms of these coordinates, theta or whatever, in terms of some finite distance, this is actually an infinite affine distance. This patch, which looks like a finite coordinate distance on this coordinate patch, is actually an infinite affine distance because it's a distance, it's the distance all the way up to infinity. So this region of the diagram is actually like flat space. So this is past null infinity, this is future null infinity, and this patch here, basically has infinite extent. I can cut off the patch, so it doesn't go all the way to infinity, and even then it has some very large extent. Okay, so this has erase this and I'll do this. So this patch or let me actually say it in a different way. Sorry. Think of an observer who crosses, and I'll say the same thing in an even more physical way. Think of an observer here, okay, who's crossing, who's living, who's doing something like this. So there's some observer who's trying to cross this initial data. Okay. The time it takes for him to cross this patch requires this patch is very large in terms of physical distance. So the distance from some finite coordinate zeta to the point zeta equal to pi by 2 is very large in terms of coordinate distance. Okay, so this is just to explain what's happening here is I'm saying I'm turning on some source. I'm turning on some source along past null infinity. The source is sending out some light rays, and there's some observer who's trying to cross all of those light rays. These light rays for this observer look like they're very dilute light rays. It takes a long time for the observer to cross, all this very large beam. It's a very, very broad beam of light. Okay? But now, look at this. The same beam is propagated along lines, along null rays like this. And then the same beam ends up here. So it's going to now hit this observer who's trying to cross from the outer horizon into the inner horizon. Right? But this time, you can check, is very finite. This is not an infinite amount of time. So this light ray, which was here, spread out, had a large number of oscillations and was spread out over a long time, has got compressed into a very short time. Okay. This is the statement that the inner horizon sees a large blue shift. If you give me initial data at past null infinity, by the time the initial data propagates up to this inner horizon, there is a very large blue shift. Okay. So this is the physical point I want to make.
I can't see the blue shift.
So the blue shift is as follows. See, you specify initial data here, okay, on some surface here, but this is a very large affine distance. Because this is a distance which is infinite. Conversely, if you have an observer who's trying to cross these light rays so as to capture all of the oscillations, it takes him a very long time because even though we've compressed things to finite coordinate distance, if you go back and look at the metric, this is actually infinite distance. Because this is all the distance to infinity. This is past null infinity and this is future null infinity. So this is the distance all the way to infinity. So there's a very long proper time it takes for this observer to cross this data, to cross all of these light rays that are coming up. On the other hand, when the observer crosses them here between r plus and r minus, it takes only a finite amount of proper time, some order 1 proper time, for the observer to cross from r plus to r minus. But if light rays are propagating, if the data is propagating along light rays, then all this data that was here, all the information of that source gets compressed into this finite proper time. So if you had a source here that was even a very low frequency source, that saw only one oscillation, or that saw one oscillation for a very large time, even then it would see an infinite number of oscillations in this period all the way up to infinity. And these infinite number of oscillations are going to come and hit this observer as he tries to cross r minus. So therefore there's a very large blue shift. If you give me some frequency here which is a low order 1 frequency, it gets infinitely blue shifted as you cross the inner horizon. Is this seriously, I haven't tried to say this very mathematically because it's hard to, it would get into too many details. But it's the physics of this here. Basically what's happening here is this distance is getting compressed into some distance which is finite. Okay? All the data that you turn on at past null infinity is seen by the observer as he crosses from r plus to r minus. Okay? So whatever low frequency waves you turn on, are all going to come and hit this observer. And that's telling me that there's an infinite blue shift as you cross the inner horizon. That's why, the moment you move slightly away from the Dyson-Ostrom black hole and turn on some small perturbations, the inner horizon collapses into a singularity. So the inner horizon is not actually a smooth place, it collapses into a singularity, and that's because there's an infinite blue shift. Okay, so are there any questions about this fact? It's a slightly subtle point, but it's a point we're going to use. This point about ray tracing and blue shifts are points which are going to come up again. So if there are questions, I'm very happy to answer.
Comment about R plus, right? I mean, this is making a comment about R plus.
No.
What happens in the collapsing shell case? Do we still have this R plus R minus 3?
So 1 second, I'm telling you what the collapsing shell is. Okay. So if you look at the collapsing shell, then here's the true diagram. So if you take the collapsing shell, then what happens is here's null infinity. I'm going to draw this origin of coordinates in this way. So my origin of coordinates here is going to be a little curved. Okay. So this is the diagram that you get in the situation where you have a collapsing shell. This is past null infinity. This is future null infinity. This is the horizon. This is the surface of the shell. This green line. If you can see the green, but this outer thing is a green line, is the surface of the shell. This is the origin of polar coordinate. There's another singularity that we have there. Okay? So really, the true Penrose diagram of a realistic collapse is very similar to the Penrose diagram we had in Schwarzschild case. So even though Dyson-Ostrom Penrose diagrams look very exotic, that's actually a bit of a fake, and they are not actually exotic. In fact, the physical situation we believe for a collapse of something with charge or angular momentum is very similar to the physical situation of collapse with a Schwarzschild black hole. Okay? So the fundamental point, the punchline, if you haven't been following this discussion, let me just tell you what the punchline is. The punchline is that everything is the same as Schwarzschild, okay? Not everything. Things are the same, things are similar to Schwarzschild. Okay. So
this horizon is R plus?
This is horizon is R plus, yes. Okay, so if you haven't followed this discussion, it is this line you should remember. Okay, so things are very similar to Schwarzschild, even though they look different in the maximum. Okay, so this is the punchline of this. Okay.
Which means that the manifold has to terminate at R minus.
It does. That's the singularity.
Which is like probably a.
There's a null singularity here.
That is R minus.
That's R minus. This is the line here. This is this line. Okay. Good. So now
It's a null singularity.
it's a null singularity. Okay, good. Now I want to quickly do.
So when was this diagram first drawn?
Oh, I don't know. I don't know when it was first drawn.
And this is very strange. The entire 0 to R minus region is gone.
I'm more
Okay.
curious about trajectories.
I mean, 0 to R minus. If you have very small charge, then the R minus is very close to 0. If you have large charge, then you get some singularity there. In general, this is very much what's happening to a Schwarzschild, to a Schwarzschild observer. You cross some horizon, eventually something becomes, you go hit a singularity. In the charge case, you hit a singularity slightly before you would have hit it in the uncharged case, but okay. I mean, there's some charge, there's some question.
About a null trajectory, so basically what will happen if you have a null trajectory falling in?
You would still hit that singularity. There's an origin of polar coordinates, so you can bounce off that, but you would still hit.
Bounce off.
But the origin of, what does it mean to have null? This every point here represents an S2. So a null trajectory, what you actually mean is a collapsing shell which is collapsing at speed of light. So it collapses down to 0 and then it will collapse out. So that's what is called bouncing off the origin of polar coordinates. Okay, good. Now, I'm running a little behind time. Okay. So we have about 20 minutes, so let's try and do I'll give you one more result. Yeah.
Small perturbation to the RN.
Correct. Yes.
Now what will the metric become?
Oh, the metric you can solve in perturbation theory. I mean, there's not an exact solution. You take the Reichenau-Strauss setup and try and solve it. Okay. So let me just tell you, by the way, the situation for the ADS-Schwarzschild case, the causal structure for the ADS-Schwarzschild case. You see, the ADS-Schwarzschild case, once again, if you look back, we have to introduce the tortoise coordinate. The tortoise coordinate is very useful for getting the causal structure of all of these solutions. The tortoise coordinate that you introduce there has this form. Okay. So what's the behavior of this tortoise coordinate, by the way? As you have right. So there's some horizon here, which is the root of this thing. Yes. So what's the behavior of this tortoise coordinate? Can you tell me what the behavior of this tortoise coordinate is? Right, so at r equal to RH, where RH is the root of this, it goes to minus infinity as usual. What happens at infinity? Right, it's finite. You see, it's finite because when you try to integrate this is actually a convergent integral towards infinity. So it goes to some constant at infinity, and you can choose that constant to be 0. So the tortoise coordinate here has this behavior. Okay? If you integrate this equation and choose the constant of integration properly, you can make it go to 0 at r equal to infinity, and then it goes off to minus infinity at r equal to RH. Okay? So what happens now? You see, you get exactly the same Penrose diagram, exactly the same Kruskal diagram as we had in the ordinary Schwarzschild case, but with one important difference, which is the following. I'm going to leave this because in the ADS-Schwarzschild case, we drew this causal structure, and this causal structure had this form of singularity. Singularity at the bottom, these horizons. Do you remember this from our Kruskal diagram? If you turn your pages back to the first lecture, we discussed the Kruskal diagram of the Schwarzschild black hole. So everything is the same except for the fact that r star doesn't go up to plus infinity. Okay, r star doesn't go to plus infinity because of that. See, r star goes to a finite number in this case. So you get a boundary. Okay, r star. This boundary is so this is uv equals plus 1, and then there's a boundary here, which is uv is equal to minus 1. And this asymptotes to the horizon. Okay. So this is called the boundary of space. And the reason you get this boundary is because you see the space ends at r star equal to 0. So in the Schwarzschild case, you had all the region to the right of this and to the left of this, but you don't have this region in the ADS-Schwarzschild case. So the ADS-Schwarzschild case is like the Schwarzschild case, except it has a boundary. And sometimes you will see this drawn as a Penrose diagram rather than as a Kruskal diagram. As I said in the first lecture, these things have the same information. But if you draw this as a Penrose diagram, and sometimes this solution is drawn as follows. Okay. So if you compactify this and instead of drawing hyperbolas, you like to draw Penrose diagrams, you can make your tan inverse changes and you'll get something like this. So this is the Penrose diagram, this is the Kruskal diagram, and they are giving the same information. Now, the physical significance of this, and actually tells you why ADS is useful, is that working in ADS is like working with gravity in a box. You see, adding a cosmological constant gives you a boundary, so it's a natural way of confining things to a box. So if you want to study gravity in a box, the correct way to do that is to study gravity with the negative cosmological constant. Okay, so if you really try to put gravity inside a physical box, that's something that's hard to do because you can't impose boundary conditions which are general, which transform well under general coordinate transformations. And that's the statement that in general gravity waves will make your the walls of your box oscillate. So if you want to confine gravity to a box, that's not so easy by just cutting off space. But the correct way to do that is to think of things in anti-de Sitter space. And as you can see, by putting things in anti-de Sitter space, you get this solution, and this solution is a black hole in a box. So the ADS Schwarzschild solution is the Schwarzschild solution in a box. Okay, so this is the statement I want you to get here.
What happened in de Sitter? Can you have a change in?
Yeah, so de Sitter is more complicated. It has it's much more complicated. So let's not discuss. And we can discuss de Sitter a little later. De Sitter is someone asked the first question. You asked the question. Yeah, so we can discuss. Let's discuss de Sitter separately. De Sitter is a more complicated story. It has cosmological horizons also and other things. So but anti-de Sitter space is very simple, and it's something which is gravity in a box. And we're going to use anti-de Sitter space. Okay, so in this situation, things are similar to Schwarzschild. The Schwarzschild in a box. Okay, good. So that actually brings me to the end of the causal structure. Now I want to go back to the curved black hole, which we haven't considered, and talk about some physics of the curved black hole. Are there any questions so far about the causal structure? Okay.
What do you mean by gravity in a box?
It means this. It means that there are these boundaries, and therefore you can go from here and come back. In some finite. You can have a light ray which will go here and come back in finite definite distance. So there's a boundary. So the boundary is a box. It's like confining gravity to some finite distance. The finite distance precisely means you can send a light ray that will come here and come back in finite time. So you can have an observer who sends a light ray that bounces off the boundary. We have an observer here. He sends a light ray that can bounce off this boundary and come back. You can check by using this metric that you can take a light ray that will bounce off the boundary and come back in the finite lifetime.
So when you introduce this box, when you put a boundary on it, what about the Lorentz invariance of everything?
So that's why when I said box, I said it's box with a cosmological constant. What the cosmological constant is doing is confining things. So I'm not really putting a box. If you try to put, that's what I said. If you really try to put a box on gravity, that's a bad thing to do. But if you have a cosmological constant, it confines things to some finite area. So cosmological constant prevents things from going out to infinity. That's the significance of working with a cosmological constant. It's a smart way of putting gravity in a box.
If I manage to take n to infinity in some sensible way, then I can get back to the results I have.
That's true. Yes. Then you'll look like you're If you look at physics, which is this is a big black hole. If you look at small black holes, they behave a lot like black holes.
So these regions are still like 1, 2, 3, 4 of the.
Yeah, there's exactly regions 1, 2, 3, 4. They're exactly the same. Everything is the same. 1, 2. Except that regions 1 and 3 are cut off. So regions 1 and 3 are cut off by these boundaries.
So the space, volume of the space is also finite.
The volume of the space is not finite. The volume of the space is still infinite. If you use a Cauchy slice here, you talk about volume. If you talk about slices, the volume of that space is still infinite. The volume is not finite, but it's true you can still send a light ray and get it back. So the volume is not finite.
So I can send a light ray in finite time, but can an observer move on a time-like trajectory?
No, an observer can't move on a time-like trajectory and come out because it requires infinite energy for the observer to reach null infinity. See, because it's a box, the only thing that can really climb out is a light ray. Some time-like trajectory can't quite climb out of the potential, but a light ray can climb out and come back in. A time-like observer can't. We'll discuss the geometry of ADS maybe a little more in some detail, but I just wanted to show you this thing. Anyway, I'm happy to answer more questions about this geometry. Okay, good. So now, good. So let's look at the Kerr solution. So what do I want to say about the Kerr solution? So do you have the curve solution in your notes from last time? Do all of you have? Let me. Okay, so just look back at the curve solution. I'm going to start by giving you a by making some statements. In defining the curve solution yesterday, I used this thing called delta. I'm going to tell you where the horizon is. To analyze where the horizon is, you really need to do some global causal analysis and draw the Penrose diagram. But it turns out the horizon delta equal to 0, which is r plus a squared plus b squared is twice r. So now I'm going to go to the curve solutions. So the first statement, this is a fact, I'm stating the horizon is a delta. The second thing you can check is that the horizon is not where dtt is 0. Okay? And the third thing you should check, this is a tutorial question. Constant omega, so this is a different omega, it's not the sphere omega. This is just, this omega is called the angular velocity of the horizon. It has the form r plus square, where r plus is the larger root of this. R plus is the larger root, and omega is defined as this. So this is a simple exercise in taking the metric we wrote yesterday and checking that if you look at d by dt is not necessarily null, but there are two killing vectors of that metric. One of them is d by dt, the other is d by d phi, and a particular linear combination of d by dt and d by d phi. The linear combination is when you take this omega equal to this, becomes null at the horizon. Okay, so this is a simple exercise in taking the metric and working out the vicinity. Okay. Now, by the way, I'm assuming that all of you do have the notes from last time and you have the metric. So we can, you want me to write the metric again? It's some.
So here also this key variable is the m satisfied.
Here also, that's right. So here also you have an extremality condition, which is that m square has to be greater than a squared plus e squared. So you can check, what happens for this to have roots, and it has to be that m square is greater than a squared plus e squared. That's when this quadratic equation has roots. So there's an extremal condition in the curved black hole. Okay. Now, the next statement I want to make is that you can check that there's in fact a region outside the horizon, okay, where this d by dt itself becomes space-like. D by dt goes to 0 and then becomes space-like outside the horizon. And that region is what's called the ergosphere. So it turns out when you look at the horizon, which is at some value of r, there's a region outside the horizon and that's because if you look at the metric of the d by dt term, you see the metric of the d by dt term. Let me just write down what gtt is. d by dtt is this term. It's delta minus a squared sine square theta by sigma. Okay? This term you can see there's some delta here. So before delta becomes 0, this term can become 0 because there's some a square sine square theta. Of course, at theta equal to 0 and at theta equal to pi, this term coincides with the horizon. Okay. But this term can become 0 before delta becomes 0 because there's an additional a square sine square theta sitting there. So especially if your theta equal to pi by 2, okay, this term can become 0 somewhat before the delta becomes 0. And this region outside, which is the region where delta minus a squared sine squared theta is smaller than 0, is what gives the ergosphere. So this is the region where delta minus a squared sine squared theta is 0, and this region is called the ergosphere. Okay. So this is the definition that you will see. Now the important thing is that the existence of the ergosphere allows you to do something very interesting with black holes, which is that it allows you to extract energy from black holes. And the process of extracting energy from black holes is called the Penrose process. Now why is this surprising? You see, you might have thought that black holes were things in which things can only fall in and things can't fall out. And so you might have thought that black holes have the property that you can throw things in and therefore the mass increases and the mass keeps increasing. There's no process you can do that will reduce the mass. Because that's what we think of a black hole. We think of a black hole as something from which mass can't decrease. But it turns out that the existence of the ergosphere allows you to define a process which is called the Penrose process, which allows you to extract energy from black holes. And that process is as follows. So for this, things are not to this one shared. So use this mark now. This is the process where you have a particle that comes in. Okay. So here is P in. It comes in with some momentum P in, and it goes out of the ergosphere. But it splits, it ejects some part of itself. So a particle that comes in and breaks into two, P out 1, and this is P out 2. So you have a particle that comes into the ergosphere, it splits into two parts. One part falls into the black hole, the other part goes out. Okay? And I'm now going to show you that in a process of this kind, you can actually end up in a situation where energy that you have here is larger than the energy you have here. How many of you have seen a description of the Penrose process? Oh, very few. Okay. So then I'll go through it slowly. Debashish, did you say you want to talk to the students now? So you want to be strict about time today? Okay, good. so then this may be a good thing to discuss for next time. Okay, let me just give you the motivation for the Penrose process, and then I'll stop. So here's how the motivation for the Penrose process works. You see, imagine some particle on some trajectory, okay, which is moving. And how do you define the momentum of the particle? The momentum of the particle is defined as, okay, this is the definition of the four momentum of the particle. Now, in general, not all components of this four momentum are conserved because we are not in flat space. Right? So we are not in flat space. So in general, we don't have symmetries in all directions. Not all components of the momentum are conserved. Remember that momentum conservation has to do with symmetries of space and has to do with the existence of a, some nodal charge. So momentum in here is a nodal charge for a Lagrangian of the point particle, and the fact that momentum is conserved tells us that we are living in a space-time where you can translate in x and physics will be the same. Of course, in this situation, it's not true that you can translate, for example, in theta and physics will be the same. Right? Or it's not true that you can translate in r and physics will be the same. So not all components of this momentum are conserved, but some components of this momentum are conserved. Okay? The components that are conserved are the components where we call this K. So K is d by dt and r is d by d phi. So if you look at P mu, K nu, G with a minus sign. The minus sign is because of the sign of the metric that we're using. Okay. That's because k nu is a null vector. Sorry, is a killing vector for the geometry. Because k nu, which is d by dt, is a killing vector for the geometry. T dot k, this a component of the momentum, which is the energy is conserved, and P mu, R mu, D mu, which is the angular momentum, is conserved. Okay. So you have a particle that goes in, it comes out, it conserves this part of, particle goes in, it comes out. You expect that the total energy is conserved and the total angular momentum here is conserved, and other quantities, other components, we're not saying. So if you have a particle that's moving as a flow, it still has these two conserved charges, which are these two conserved charges. Okay? Is this fact clear? There are two killing vectors. So there are still two symmetries that we have, which are these symmetries under K and R. So these two are conserved. Okay. Now this particle comes in and it breaks into two parts. Right? That means at this point you can write down some local conservation of energy and conservation of angular momentum, which is where this particle breaks into two parts. So we have E in 1 is equal to E out 1 plus E out. Where 2 is this particle and 1 is this particle. Okay, so this is 1 and 2. This is particle 1 is still coming up. The thing that comes out I'm still calling particle 1. It's like the spaceship went in, it threw in some stuff there and it came out. This is particle 2. Okay, so is this clear? These equations suggest local conservation of energy and angular momentum. We want, for particles in, when we say that something has to have positive energy in some region of space-time, what is it that we want? You see, what we want is that if you have some slicing of space-time, and there's some time-like vector, then with respect to that time-like vector, they have positive energy. Right? When we talk about positive energy, what we are saying is that with respect to some particular time-like vector, they have positive energy. Right? But d by dt is not time-like in this region. D by dt is not time-like in this region. So there is no necessity that E2, which is defined as the form momentum of P projected onto d by dt, has to be positive. Therefore, E2 doesn't have to be positive. Okay? So, because d by dt is okay. So, this you can have a particle which looks locally like it has positive energy. But in terms of what we've defined as E out, which is the projection of the momentum onto d by dt, this can be negative. Right? Therefore, E out too can be negative. So we see that you can have a situation where E out 1 is greater than E in 1. Is this fact clear? I'm going to give you a constraint on this in a minute, and then I'll stop. But you see, you can have a situation where the energy of the outgoing particle is greater than the energy of the ingoing particle. That's because in this process of things breaking up, you can have something which locally has positive energy, but in terms of this definition of E, still doesn't have positive energy with respect to its projection of the momentum onto d by dt, because d by dt is a space-like vector. So things can have negative space-like momentum. There's no constraint saying that particles have to have positive momentum in all directions. They can have negative momentum. They just have to have positive momentum in time. Right? So the local notion of time here cannot be d by dt because d by dt is space-like. So there's no constraint in having E out being negative. Is this clear? So this process is called the Penrose process, which allows you to come up with a situation where you have more energy outside than you have energy inside, And of course, by conservation of total energy, the mass of the black hole has to decrease. So you have extracted energy from the black hole in this process. Okay. However, not everything is for free because there is some constraint. There's some constraint. And what is that constraint? Can you extract an arbitrary amount of energy? Is there some constraint that you can see? Right. So angular momentum conservation is there, and you see the fact is that there is a time-like vector inside. It's not true that you can do whatever you like. You can make d by dt. You can make this projection onto d by dt arbitrarily negative, and that's because there is a time-like vector. That time-like vector is the vector we discussed a minute ago, which was the vector. The fact is that d x nu by dt of the second particle of d tau into k nu plus omega h into r nu with a minus sign has to be positive. That's because this vector, which is the d by dt plus omega h into d by d phi, this vector is still a time-like vector. So this vector I can use as a good time-like vector. Okay, so with respect to this time, which is a good time even inside the ergosphere, this vector you can take as time-like even here. Energy has to be positive. So it must be the case that the projection of the form momentum of the second particle on this vector is positive with a minus sign in front. Okay? This has to be the case because this is locally a time-like vector, and if I look in any local time-like direction, it better be the case that energy is positive there. Is this clear? Okay? This tells you that you must have, once you put in the minus signs, you see this gives you E2 with a minus sign, and this gives you minus L2. Okay? So it tells you that E2 out minus omega h L2 out is greater than or equal to 0. Okay. Which is the statement that if you look at the change in the angular momentum and the energy of the black hole, you see L2 out gives you the change in the angular momentum and the energy because this is what has entered the black hole. It's a statement that delta L is smaller than delta E by omega h. Okay, and there's no statement about magnitudes here. Okay, it's just a statement as follows. If delta E is negative, then delta L has to be smaller. If delta E is positive, then delta L has to be smaller in magnitude. If delta E is negative, then delta L has to be larger in magnitude. It's really, there's no absolute value sign. Okay? And this constraint comes from the fact that the second particle that broke off here has to have positive energy with respect to this scaling vector, which is d by dt minus plus omega h into d by dt. Okay? So this is the constraint that we have. And so you see that what you're doing when you're reducing the energy is you're also changing the angular momentum. Okay? So as you reduce the energy, you also reduce the angular momentum. And you reduce the angular momentum by an amount which is, which is larger in some sense in some units of omega h. Units of omega h is 1, it's larger than the energy reduction. Okay? So there's some constraint you have in processes you can do. You can extract energy from black holes, but that's only if they have angular momentum to start with. Okay? If you had a small-shell black hole that had no angular momentum, you can't extract energy. If black holes have angular momentum, you can play around, you can trade off the energy and the angular momentum to reduce the angular momentum in such a way that you get some energy out. Now tomorrow we'll discuss this, on Monday we'll discuss this and show how this leads to the so-called laws of black hole thermodynamics. But I'll stop here with this. Are there any questions at this point?